picture from my mom. She believes that I actually was here. If you want to be waving in the picture, this is your chance.
Hi, Mom.
Awesome. She will be very happy. Okay, so thanks for having me, and thanks that you were all here. It's really nice. I'm having a great time. And I have a confession to make. So I do very little concurrent programming and async programming because I think it's actually very challenging. So the funny thing is, I'm working on a new Mac app together with my friend Florian. He also writes this magazine with me, Objective-C.io, and last week we were debugging our app, and we had this thing where we generated a PDF. And the problem was that sometimes it didn't work. We didn't really know what was going on. We were just generating this PDF, and most of the time it was completely fine. The first time it was often some kind of a little bit weird. The first time, or the first page of the PDF was some kind of problematic, but then if we scrolled a little bit in our document, then it would work. And this was very challenging, and it started at the beginning of the week, and at the end of the week we still had the problem, and then we decided to solve it. And it took us maybe 4 or 5 hours. And what happened is we had an NS document on the Mac, and we were generating this PDF the moment the document data got loaded. And this callback was not on the main thread. We didn't know, but this is like exactly the kind of problems you get when you do parallel programming. So a lot of the code on the Mac is not thread safe, or makes assumptions that you are in the main thread, or maybe sometimes assumptions that you are in a different thread. And all the really good programmers I know have problems with this. So it's a word of warning. So with any time you do parallel or async programming, you need to think about these things and think about all the problems you might have. And also when you're not doing async programming, or when you're thinking you're not doing async programming, think about these problems. They might cause bugs for you. Okay, so this is the kind of code that we wrote actually to solve our bug at first. This perform selector update with object after delay 0. You might, if you did JavaScript, at any time you might know like window.setTimeout and then a function and then 0. And then everything works magically. And actually, I stole this code, I modified it a little bit. I stole it from Peter. And he mentioned it as a thing that you should never do. And it's true, and we did this and it solved the problem for a little while, but not really. You should never do this thing. This is always a sign that you're probably doing something wrong. I write this code sometimes to fix my problems, but if you see this code in your own, if you see this statement in your own code, then you probably have a threading problem. A different way to write this is this. This is actually, I literally copied this from Peter. So dispatch async, dispatch get main queue, self-update. If you are already on the main queue, and then you write, you know that you're in the main queue, and you write this, then you also have a problem. So this is another example of what you should not do. And this is the really nice, complicated way to do the same thing. So this is dispatching after 0.1 seconds. So just like after your view rendering is done, or after auto layout is done, you do this. So anytime you see this, take it as a word of warning. And well, like I said, also a lot of good programmers write this kind of code. It's not a problem if you write it, but just think like, what can I do to make sure I don't have to do this? Okay, so I want to talk about some practical issues, like these ones, and then show some of the potential problems you might get when you do parallel programming. Because I think it's very important to make sure you're doing as little parallel programming as possible, or async programming. Like I said, it's really, really hard to debug, and it's really makes your code very complicated. However, sometimes you need it. And these are some of the reasons. For example, if you are scrolling and it is too slow, then you might need parallel drawing. If you are doing network requests, then it's also very important that you're not doing that on the main thread, and that you're not blocking the main thread. And if you're importing data, for example, if you have a big core data application, or if you need to load a lot of data, and you're doing it on the main thread, then your app might get very unresponsive, and this is also not what you want. So, only when you really have a problem, you should do this stuff. And conceptually, it's important to think about what you are parallelizing, or what you are doing asynchronously. So, sometimes you might want to parallelize the GPU stuff. In other times, and this is, I guess, most of the time the problem, you want to parallelize things that are happening on the CPU. If your CPU is very busy and is doing a lot of work, for example, on the main thread, you want to make sure you split that up into multiple threads so that your main thread doesn't block. Other times, it might be areas in your memory, like, for example, a special kind of number that you are sharing. And sometimes it's files. So it's always good with any async problem to think about, like, what am I trying to make asynchronous and what am I trying to not block? Yeah, and then the question, why is this so hard? Because, yeah, everybody knows it's hard and everybody has problems with it, but why is it like that? So this is what I always do. So I write some code, then I run it, and I test it on my device, or sometimes on simulator, and everything works. However, if you're doing async programming, sometimes it doesn't work. So you might say, well, Chris, you're doing it wrong, you should do it like this. So you write a unit test, you make it fail, then you write the code to implement it, all tests succeed. And you might still have bugs. And this is, for me, the problem with parallel programming. The bugs are really hard to find. And you need users in the wild using your app that find those bugs. For example, it might be that you're developing with a test server, like a web server, and everything is very fast because the web server is on your machine. However, if your users are using your app and they're driving in a tunnel, it might take a minute and a half before the request times out. And if we're doing that request on the main thread or on any thread, the thread will block. So that's why it's so hard to work with this parallel code. You might still have bugs. And because parallel code is non-deterministic, it's very hard to test. You never know which path is going to be taken. And we'll discuss this a bit later, but there are lots and lots of tricky problems. Once you do make your code parallel, you will probably introduce new problems. Okay, and this is, I stole this from Apple. And it's another thing that's really good to remember. Before you even start on this, just make sure it's really necessary. And yeah, you can take these steps. So if you have a problem with the responsiveness of your app, you can take these steps to make it faster. So first, you determine what makes your app so slow. So you think about it, and you think you know it. And then the really critical step, which I think I often forget, and also other people I see often forget, is measure it. You really have to make sure that what you think is right, and you have to measure what is making your app slow. So you can use instruments or sometimes log statements, but make sure that you're going to optimize and fix the right thing. Then you can take that code that is making it slow and isolate it. So maybe in a different class or in a different method. And then put it on a queue. And then you measure again. And this is also very important, because you want to make sure that what you did actually made a big difference, or a difference. And that's the basic recipe. Okay, so let's talk about some of the problems you might have and some of the solutions you could take. So your scrolling is too slow. And this is a very common problem. And now with the 5S, it's less of a problem because everything is really, really fast. But this is one of those things that iOS developers generally like. I think we want to be proud that we have really smooth scrolling. And the reason why your scrolling might be too slow, there might be a lot of reasons actually, but almost always it's drawing. So if you imagine your main queue, or your main thread, this is what happens. So first, there's some drawing, and then maybe you do really complicated drawing that takes a lot of time. Then there's some core data stuff that might happen, and maybe a URL request that gets handled, and some more drawing. And only then does the input, does this stuff get rendered, and does the input of the touches get handled. So as long as you're doing complicated stuff on the main thread, your app cannot really scroll. So depending on what it is, you might want to take that code that's complicated out and put it somewhere else. So in case of drawing, it's actually quite simple. So the thing here to realize when you're drawing, you're probably doing it with core graphics, and it's probably all being done on the CPU. And that's, again, good to remember what you're parallelizing. So the way we solve this is we take the drawing code and put it in a different queue. It's as simple as that. However, there's of course a slight problem. UIKit is not thread safe. And there are very good reasons for that. UIKit only works on the main thread, and that makes it very fast. But if you want to do things in parallel, it makes it a bit more problematic. The nice thing is that if you're drawing, if you're for example doing draw rect, you can do that in a different thread. So core graphics, you can use it on any thread you want as long as it's always the same thread. So what we're going to do is we're going to take this draw rect code and put it into its own operation. And then you take the original view that you had with the complicated draw rect, and you just replace it by a very simple UI image view. UI image views are great, they're really fast. And then once your drawing is done, you update the main thread. And it's as simple as that. So before you had this, so you had draw rect and then the really expensive drawing code. And if you rewrite it, you write it like this. So suppose you have this queue, we'll talk a little bit later. We'll talk later about how to get them. Suppose you have this queue, you just add an operation in the block. And then you say UI graphics begin image context with options. And this creates a new drawing context on the thread you are on. And there's a nice little detail. This 0 here is the scale. So you can pass in 1 or 2. So 1 for a normal display, 2 for a retina display. And if you pass in 0, UIKit will detect which display you are on and use the right scale for you, so you don't have to do that. Then you do all your drawing code, and then you can say UI graphics get image from current image context. And then you get a UI image out. And then the important thing is that after you have this image, which you created in your own queue on a separate thread, you go back to the main queue and then update the image view. And this is it's as simple as that. I did it a couple of times. In most of my applications, or in most of anybody's applications, I think this drawing is not a problem. But if it is, here's a very simple recipe for how to do it. So, another problem. Loading an image over the network. And this is, there is also a lot of misunderstanding about this. And I will also show some of the things I did wrong myself. So this is a really cute example. And I wrote this code. I did it like this a few years ago. So when Grand Central Dispatch came out, I wrote my image loading code like this. So you say dispatch async on a background queue, and then everything inside that block gets done on a background queue. Then you say image data is data with contents of URL, and that's a blocking call. However, what I always thought, it doesn't matter because it's on a different queue. Then you say image alloc init with data, image data, and then you have your image. And once you have the image, you go back to the main queue and update your image view. But there are a lot of problems with this code. One is that it's blocking, and another one is that you cannot cancel it. So, does anybody know how to cancel something like this? No hands. Or what happens if this request times out? So what if this data with contents of URL, what if this gets done while the user is in a tunnel or in an airplane, and it takes 90 seconds before the request times out? It's really good to think, like, what could happen? Well, actually, the current thread gets blocked until it's there. And to understand why this is a problem, we have to look at Grand Central Dispatch. So this is how it works. I hope you can see the bottom part in the back. So Grand Central Dispatch has the main thread and the thread pool. And this thread pool is like real operating system threads that gets managed by Grand Central Dispatch. And then there are some queues. It's a bit hard to read. So there's the GCD main queue, and everything you put in that queue gets executed on the main thread. And there are 4 other queues: the high priority queue, the default priority queue, the low priority queue, and the background queue. And they're all very special except for the default priority queue, which is the one you should always use. If you create a new custom queue, it will always use this default priority queue. The high and the low priority queue are, they seem like a good idea, but you get also really weird problems if you start using them. We'll talk a little bit about that later on. The main queue is a serial queue. So Grand Central Dispatch distinguishes between 2 types of queues. So either serial, everything you add there gets executed in order, or parallel, and then it gets executed at the same time. So if you remember our example where we had this data with contents of URL in a background queue, this background queue was parallel. And it goes to the default priority queue, and because the default priority queue is parallel, this blocks the queue or the thread that it's on. If something new gets into this default priority queue that also wants to run, Grand Central Dispatch has to create an extra thread. And that's really problematic, because extra threads are very expensive. So yeah, this is the problem. If the request is blocking the queue, you get a lot of extra threads. And we want to avoid that. Because suppose you're doing a table view with scrolling images, for example a Twitter client with user profile pictures, then as you scroll, a lot of threads gets created. And that's not a good thing. So what can we do? We're going to change our codes, and instead of working with Grand Central Dispatch, we're going to work with operation queues. And operation queues are an extra Objective-C layer on top of Grand Central Dispatch. So you get to use all the nice things of Grand Central Dispatch, but just in Objective-C. So we're going to rewrite this code. So the first step is to use NS operation. And you use NS operation like this. It's almost exactly the same as Grand Central Dispatch. So instead of dispatch async, you create this download queue, and then you say add operation with block. You load the image data, you create the image, and then on the main queue, you set the image on the image view. And this is a first step. Now we still have the problem that we cannot cancel this. Because there is no reference to this block of code. And if we want to cancel it, we can use an NS block operation. So an NS block operation you create like this. You say download operation equals NS block operation block. You add it to the queue over here. And then whenever your user, for example, when you stop scrolling or when your table USL gets out of the screen, you just say download operation cancel. And it's as simple as that. So this is the main reason to use NS operation queue instead of grand central dispatch, because you can find and cancel things. Another nice optimization that we could make now is pull out the completion handler. So this is the same code still, but NS operation has a completion block property. And if you put this main queue stuff in a completion block, then you can take another refactoring and create your own NS operation subclass. And this is a pattern that I use a lot. Like, as I said, I hardly ever do parallel programming. But when I do, I try to create my own operation subclasses and isolate all of that stuff into its own operation. And I showed it now for downloading images, but this is also for data processing. You might have the same problems if you, for example, processing a JSON file and you're doing a lot of heavy computation. You can put that in its own operation and add it to the queue. And now we have a really nice object-oriented way of doing this. So I see some puzzled faces, because you might be thinking, well, Chris, you're doing it completely wrong. And you're right, because actually in this example, we should have used NSURL session for this specific example. And NSURL session is as simple as this. We just say download task with URL and a completion handler. And it's of course a lot better, because now we have asynchronous networking and we don't have to worry about all this stuff. But the point is that if you're doing things async, that's not networking and that's not provided by Apple, then use operation queues instead of grand central dispatch. This is only in iOS 7. In iOS 6 you would use NSURL connection, and it's the same thing. You should of course use that instead of my example with operation queues. Good. Another problem. You want to import a large dataset into core data. And if anybody has questions during the talk, also feel free to interrupt me. We just talked about this over coffee. This is a very common problem, and people have a lot of problems with core data and async stuff. And there are some ground rules, and if you just follow them, it's actually not that complicated. So this is a normal core data stack. At the very bottom you have an SQLite file. On top of that is an NS persistent store. Then there's a persistent store coordinator, which manages the persistent store. And then there's your manage object context. And in your manage object context you create all your objects. The problem with the manage object context is that it's tied to one thread. So if you have a manage object context that's on the main thread, you can only use that on the main thread. If you start using it on other threads, things go horribly wrong. So what can we do? So if we have very simple things that we want to do in parallel, we can create a second manage object context. And it looks like this. So it has the same persistent store coordinator. And to do that, you write this code. So you say manage object context alloc, init with concurrency type, private queue concurrency type. And this is a new API. And you set the persistent store coordinator. I made it a bit shorter so it would fit on the slide. Oh, there's something went wrong with the code. So what's important is that for everything you do in this context, you say self.context before block. So this private queue concurrency type parameter makes sure that the context creates its own queue. And then if you say before block, anything inside that block gets executed in that queue. And it's really important that you stay in that queue. So you just say self-import. What you should probably not do is talk between this private queue and the main queue. If you start talking between two managed object contexts, things get really complicated, and it's probably a design mistake. I do this sometimes, and then I always know I have to fix my design. What you probably should do is you do everything on the main queue, and then only if you have something that's going to take a long time or is complicated, you create this private queue, and you do all the work isolated in that queue. So don't talk between those queues. If you then are done with your import operation, you save the managed object context, your private context. And then you can do this. So once the object context saves, a notification gets generated by core data. It's the NS managed object context did save notification. And this is how you can listen to that notification. So you get this callback, and then you update your main context with the changes. And they made it very simple. So you just say manage object context, merge changes from context to save notification, and you give in a notification. Of course you do this in a perform block, and then it gets executed on the main thread. And there's an extra if check to make sure things are not on the wrong context. Yes?
So merge changes from context did save notification. Is it like a built-in core data API?
Yeah, so the question was, is this merge context from did save notification built-in core data API? And it is. It's really not something I wrote in my spare time. This is actually code from a project that I have. The only thing that I changed in the slides is I don't use this add observer for name using block, but I use it with a callback, with target action. And this is how you can do core data in a separate thread. But of course, there's a problem. So what happens is, if you are in your new managed object context, once you try to do stuff, the whole stack will lock. So the managed object context will lock the persistent store coordinator, which will lock the persistent store, which will lock the SQLite file. And this is also what Apple says, that's just a problem. Because now if you try to use this managed object context, everything is locked. And what they actually say, if you're doing really large imports, you should go take another step and have two completely different core data stacks. So that looks like this. So you create everything new, and then the only thing that gets locked is the SQLite file. And you might think, oh, this is a problem if I want to read out records. Well, the persistent store is really smart, and it has a row cache, so anything that was already in cache gets used automatically. It falls back to SQLite very little. So in practice, this is a really nice technique. Of course, there are some problems. So if you're, for example, using a fetch results controller and automatically updating your user interface based on core data changes, if you're doing a really large import, the fetch results controllers will go crazy. So what I would recommend there is instead, once you start doing your import, you send out a system-wide notification and stop your fetch results controllers, and then once you're done, or once you stop saving, then you send a notification and you refresh your complete UI. If you are having these kinds of problems with large imports, then you will probably know this stuff, but it's good to know. It's all tricky stuff. Okay, so this was all the practical stuff I have to say. Then there is some more things, because now you know like how to do everything concurrently, and now you're going to have more problems. So one of them is locking. And I made a small example. It's of course everybody uses this example, but I think it's a really good way to illustrate what could go wrong. So suppose you have an account object, and your account has a balance and a method transfer. And the transfer method you use to transfer money from one account to another account. It's very simple. The transfer method looks like this. It looks at self-balance. If you transfer X euros, it takes X euros off the self-balance, and then it looks at the other balance and adds the euros. Of course, in real life, it would be a bit more complicated. But the thing is, if you imagine what would happen if you have two threads calling this method, and then things can go horribly wrong. So before we look into what happens, first I want to rewrite this to show how the compiler sees this, because it's actually, this is the same code, but a little bit more clear order. So what happens first is the self.balance gets stored into a temporary variable. This might be in assembly, but this is how the compiler sees it, and then it gets updated. And it's the same for the other balance. So now we can go through and see what happens in this code. This is the single-threaded scenario. It's very simple. So you have two variables, A and B, so two accounts, and account A has 100 euros, and account B has 0 euros. Now you say, on the top it says transfer 20 to B. So you transfer 20 to B. So the first thing that happens is this current balance from A gets stored into a temporary variable. And it's 100. Then A.balance is 100 minus 20. So now the A.balance is 80. And B is still 0. Then the next step the code takes is it updates B.balance. And now we're done with our method. And A has only 80 euros, and account B has 20 euros. So everything is fine. But you, of course, see that there's a lot of white space here. And if you fill it up, you can see like what would happen if a different thread would call this method. So suppose this second thread starts, and it reads out the current balance. It sees 100, and then the threads, the first thread gets scheduled. It also reads out the balance 100. The first thread continues. It says the balance is now going to be 80. B's balance is now going to be 20. And then the second thread comes back again. And it thought, when it started, that the balance was 100. And now it will update it to 70 and 20, and somewhere euros got lost, or actually created. And again, the hard part about async programming is, normally if you test this stuff, everything will work fine. But sometimes it doesn't. And it's those sometimes that we care about. So what can we do to solve this? We can add a synchronous statement. This is this nice feature from Objective-C. And we say synchronize self, and then do this stuff. And what now happens is, if you have this A account, it will put a lock, and only then execute this code. However, you need to pass in something to synchronize, which is used for the lock. However, if you call the same method, but with the parameters switched, so if you transfer from B to A, then this lock doesn't work. So we have to add another one. Synchronized other. And now our code is more safe, but we might have deadlocks. And the point is not so much that we try to implement a banking application, but that we think about at which level we want to synchronize, and at which level we want to do parallel programming. So one point is that we have the deadlocks, and the other point is the level. So what we can do to solve this is, you can say, synchronized self.class. And now the synchronization will be done at the account level. And we don't have deadlock anymore. But we still have locking code. And another thing that's a problem, if you use synchronized, it might be very slow. So this is what the compiler sort of does. It's of course a little bit more complicated than this, but it calls all these methods and it adds 2 or 3 locks. This is very expensive, and most of the times it's not a problem, but sometimes if you write high performance code, it is a problem. And one of the things you can do whenever you see asynchronized, you can think about, can I do this, for example, with grant center dispatch? So one solution you could come up with is to have a queue, a serial queue, which does this for you. So anytime you do something with bank transfers, you put it on the serial queue, account operations, and you dispatch it async. And now dispatch async will never block, and now you can use grant center dispatch to regulate this finite resource. And it's a very nice trick. Of course, often you might want to have a dispatch sync, so you might still have synchronous things and locking and deadlocks. But if you can get away with using a serial queue and dispatch async, it's much nicer. So again, one thing to realize is when you are doing a lot of synchronization, you might want to think, at which level do I want to be concurrent? And this is, now we understand why UIKit, for example, is not thread safe. They just, if they would need to make every method thread safe and every property, it would cost, they would need a lot of logs. And they just decided to ditch this thread safety altogether because it's too expensive. And they just say to you, like, you make sure that you do it on the main thread. And if you're designing an application or a framework, it might also apply to you. So think about at which level do you want to provide this thread safety. So one more small thing with grant center dispatch, now that we are talking about async stuff. This is how you used to write singletons. And you see again the synchronized. It uses synchronized self, and in this case, self is a class. And then you check if the shared instance is not nil, and you return the shared instance. And now that we know that synchronized is expensive, we can rewrite it the GCP way, and that's like this. Again, often this doesn't make too much of a difference, but if you're using one specific singleton a lot, then it makes a difference. And this is actually what is in the Xcode default template and how Apple says you should do it. So that's another nice feature of grant center dispatch. There are some other problems you get when you do parallel programming. One is lock contention. If you use a lock a lot, then your program might get really slow if you do this a lot. And this has to do with the different levels at which you do parallel programming. You might get starvation, and you might get priority inversion. The priority inversion is, I guess, very interesting to talk about. So this is what happens with the Mars rover. The Mars rover stopped responding. And what happened is they had a task of medium priority, and they had a task of high priority. A task of low priority and a task of high priority. And the task of low priority was locking something, and the high priority task couldn't work. And then some middle priority tasks could do some more work because they were more important than the low priority task. And the high priority task never got to work. You should read up about this on Wikipedia. It's very interesting. But basically what happens is you think you define your priorities, and you think like, yeah, this is high priority, it should happen. But what, in the end, the result is that the opposite thing happens. It's really complicated. But it's very easy to introduce this. So this is a lot shorter. This is pretty much all the things I wanted to say. So what is, again, good to realize is that a lot of these problems you don't see using testing. So this is, again, a very good reason to keep whatever you're doing, make it in parallel, make it very, very simple. Make sure you understand it. You also should just use the main thread when possible. So don't try to do everything in parallel, just do things on the main thread, and only when you have a performance problem, measure it, and make sure you optimize it, and measure it again to make sure your optimization works. Don't do anything in parallel. So, when I was doing some research for this talk, my friends pointed me out to this special thing, and I thought it might be nice to end with this, because it applies. And it's the FASTA theory of software. I don't know who knows about this. Anybody? Okay. Yeah. Peter knows about it, and I hear spaghetti code. Yes. So this is a problem, right? We all wrote this, and this is one of the problems you get when you're writing software. So somebody smart came up with the idea of Lasagna Code. Lasagna Code is much better than spaghetti code. Lasagna Code is layered. So you have these nice layers. However, the problem with Lasagna Code is if you try to change one thing, you have to change it in every layer. So it's very cleanly separated, but you still have a problem. And then what they said is, instead of Lasagna Code, we should use Ravioli Code. So you have all these nice little packages, and you can modify them one by one without changing the others. So thank you. I also read this magazine, Objective-C.io. You should check it out. It's a lot of fun. And I organize a conference. If you can't get enough of conferences, come visit us in Berlin. If you have any questions about this topic or also about any of the other topics in our magazine, then raise your hand. Yes, at the back. Oh, you're just saying hi. No questions? Thank you.